Welcome to this tutorial on some of the more foundational aspects of statistics. We're going to deal today with the mean, range, variance, standard deviation, and coefficient of variation. The mean is probably the most commonly used measure of central tendency. That's the technical word for it. Central tendency just means where the data is located, right? The mean of a data set is kind of where it's located. You also get things like the median and the mode and all those kind of things. The maximum and minimum also give you indications as to where the data is located. We might deal with that in subsequent tutorials, but in this one we're just looking at the mean. And the remaining four, the range, variance, standard deviation, and coefficient of variation, represent only the spread of the data. Okay. Each are subtly different from each other. So let's get straight to it. Now, here's some things I've kind of put together already. I'm going to fill in some of this data for you in a second. But we've got a data set here. Let's have a look at this orange section. We're going to call it X. I'm asked to calculate the range, variance, standard deviation, and coefficient of variation for the following sample of data. Okay, 10 observations. Now, I can do all of this using Excel formulae, and that's what Excel is useful for. I can type in a cell. I can do it right here. Let's go right at the bottom. I can write equals standard dev. I could put all these cells in, highlight the cells, and press enter, and it'll tell me what the answer is. For the sake of you actually learning how to do these things by hand, or in other words, how they actually work, I'm going to kind of do it somewhat manually using Excel to get the range, variance, and standard deviation. So what I've got here is a few little scenarios as well as the original data set. So here's our original data set. I'm going to first calculate the mean of this sample, which I'm sure you'll have no problem telling me is just going to be the average of these. There's 10 of them, you sum them together and divide by 10. So I'm going to write equals average. Now, I'm sure you're going to have no problem doing that by hand. You add them all together, you divide by 10, and you get 15. Okay. The range is going to be a little bit different. That's the simplest measure of spread, and it's going to be the maximum value minus the minimum value. In this case, 24 minus 5. Don't use a calculator if you don't need to do it. You can do 24 minus 5 in your head, can't you? 19. Now, variance and standard deviation are related in that the standard deviation is the square root of the variance. But variance in some ways comes first, so that's why I've gone variance first here. To get it, the first step we need to think about is creating this thing called x minus x bar. Now, x bar is just another way of saying the sample mean. So here I've got 15. You might see it more commonly with the letter x and a line above it, so x bar. I'm using Excel, as you can see, and that's a little bit more complicated to put into a cell, so I've just called it lazily X bar, like that. So for each observation here, I can calculate the observation minus the mean. So for each observation, I can do the observation minus this mean value here, but you can see what I'm about to do. I'm going to put little dollar signs around the mean value that I've put in there. This is just an Excel pointer, by the way. If you're doing this by hand, you don't need to worry about this, but I'm about to drag this formula down, and I'm going to want this B6 reference to drag down with me, so that when I drag this down into the subsequent cells, that B6 will go to B7, B8, B9, etc. But this cell reference, which is my cell G6, you can't see my little cell headers and here, but trust me, that's cell G6. If I put a dollar sign around the dollar sign before the G and a dollar sign before the 6, it's going to lock that cell in so that when I drag this down, this final cell will also be referencing that mean cell up here. So it's going to be that 24 minus 15, as opposed to going 24 minus some cell, which is the equivalent number of cells down here, which is going to be a blank cell, which is a bit silly. Anyway, that's a minor point about Excel formulae. Now the next thing I'm going to do is square each of these, because you can see that these are negatives if the value of x is below the mean, and positives if the value of x is above the mean. It's 0 if the value of x is the mean. Now I'm going to square each of these. So I'm going to go that squared, which will be 100. What this does is it eliminates the negatives. And that's important because we want to try to get a sense of the spread of the data, ignoring which side they go to, right? The difference from the mean here is 10, and the difference from the mean down here is 9. So it doesn't really matter that that's negative and that's positive. It's giving us this overall picture of dispersion of this sample. So by squaring it, we essentially eliminate those positives and negatives, which is important when we take an average, right? Because you were taking an average of x minus x bar, you're going to get 0 every time because the positives will balance out with the negatives. But if we take an average of x minus x bar squared, it won't be negative. So let's find that. Now the variance of a sample, I'm not going to show you the formula here, but hopefully you'll have your lecture slides in front of you. It's going to be the sum of this column divided by n minus 1. So if I go equals the sum of all of this, and then I go divided by, now there's 10 observations. If I go divided by 9, I'm going to get my variance at 35.5. And my standard deviation is just going to be the square root of that number in the cell above. Okay, I'm using Excel formula, but I'm sure you can do this by hand. Now, a question you might be asking is, why did we divide by 9 when we were trying to take an average of this column? There's 10 observations. Why did we divide by 9? That's a bit of an advanced concept for this level of stats at the moment. So you might need to just take it on trust that when you deal with a sample, you actually have to divide by 9 due to this factor of degrees of freedom. In a sample, we have n minus 1 degrees of freedom. There's 10 observations. Therefore, there are 9 degrees of freedom. Now, if you want to check out zstatistics.com, I've got some more information about degrees of freedom, which you can look at your leisure. But it's a big, long discussion, and I don't want to get bogged down in that right now. The coefficient of variation is always the standard deviation divided by the mean. So what does it do? Why do we need why is a coefficient of variation important? Well, it kind of pegs the standard deviation to the scale of the data. What do I mean by that? Let's have a look at this. I've prepared something to explain the coefficient of variation, so bear with me just a second. It's a little bit of a tangent, but I do want to get through the idea that of what the coefficient of variation represents. So here we've got data set A and data set B. Okay, we'll go back to our original data set in a second. Appreciate that data set A is just 1, 2, and 3, and data set B is 101, 102, and 103. The standard deviation of data set A is 1, and the standard deviation of data set B is 1. And I've just calculated that using Excel formula. But you can see it's going to be the same, can't you? You've basically just added 100 to each observation to get data set B. So the spread is no different. And that's why the standard deviation is the same. The mean, however, differs. The mean for data set A is 2, but the mean for data set B is 102. So if I was to ask you which of these has the biggest spread, you could answer me that they have the same spread, but if you're talking about the actual scale of the data, look at data set A. One observation is actually double another observation. In fact, there's another observation which is triple that first observation. So it actually varies by like 100% for each of these observations. Data set B varies by only a small margin in terms of its scale, right? So that's why the coefficient of variation divides by the mean. So we take the standard deviation and we divide by the mean to get a sense of how much it varies within the scale of the actual data set itself. So there's two ways of looking at spread. You can look at spread as an absolute figure, in which case both of these data sets have the same spread, or you can look at it relative to the actual scale of the data set itself. And data set A, in that case, would have a higher spread. Why? Because you can see it doubles and triples within that actual data set, whereas data set B doesn't do anything of the sort. It goes up by a small fraction each time. Okay, that was a quick diversion. Right, so now we understand all of these factors. Our first scenario we're going to deal with, and these are the questions we're asked what's going to happen to all of these measures, the mean, the range, the variance, the standard deviation, and the coefficient of variation, if we remove the largest value. And that's 24 in this case. So before I actually show you, pause the video and have a go at trying to figure out, is that mean going to go up or down? Is the range going to go up or down? Is the coefficient of variation going to go up or down? That might be the difficult one. So have a pause and have a think about that. But if you're back with me now, let's have a look and see what happens. If we remove the largest value, now, perhaps before I do that, I'm just going to lock in these numbers here. So I'm going to paste the actual values so it won't change. Now, if I was to calculate the average of this data set, I'm going to go all the way to the bottom. There's my average. My range, I can actually, it won't let me do range, but we can figure that out ourselves. That's not difficult. The variance, using Excel formula now, just to make it quick, I'm going to go var.s. It's going to be the variance of that whole data set. .s just means the sample. The standard deviation is just stdev, and it's always a sample using that formula in Excel. And the coefficient of variation, sorry I'm doing this quickly, is the standard deviation divided by the mean. And the range is going to be the max minus the min. So if I wanted to, I can go max of all this minus the min of all this. Okay. Right, so we're now at the stage where I can remove that 24 and see what happens. So I should just be able to delete this. Book. And let's see what happens. The mean reduced. And that's no surprise, is it? Because we removed the largest value in the sample, so the mean has to decrease. The range decreased as well. We removed the highest value, so the range was somewhat reduced. Now, I'm guessing you would have also guessed that the variance decreased. Why would the variance have decreased? Well, we've taken away the value that had the largest, I can remove that too, not that it will make a difference. It had the largest difference from the mean, or largest positive difference from the mean. So in removing that, the variance has decreased. If we removed a value towards the middle of the data set, I think the variance would have gone up. But here, because we removed an extreme value, the variance decreased. The standard deviation obviously decreased with it because it's the square root of the variance. Now, it would have been tough to guess that the coefficient of variation would have gone down. You can see it has. But I don't think you could have really guessed that by, if you did, well, that's good on you. I wouldn't have been able to guess that because you knew that the mean was going down and the standard deviation was going down with it. Okay, so if the coefficient of variation is that division of the standard deviation divided by the mean, it'll only depend on by how much each of these went down. So did the standard deviation decrease larger than the mean decreased proportionately? Tough to know. So I would say it would be difficult to guess that, but in this case, it looks like it went down. You might say it probably was going to stay around the same value because both the numerator and denominator were going to decrease. Anyway, slightly moot point. So I'm just going to copy them and paste the values in there so they don't move. Now what happens if I put my 24 back into my data set? So what do you think is going to happen if I add 2 to all of these observations? Now I don't even need to put formulas in here. We can figure this out. If I add 2 to every single observation, the mean quite clearly is going to increase by 2, right? So if it initially was 15, the mean's going to go up by 2, 17. The range is not going to change, right? The maximum is going to go up by 2 and the minimum is going to go up by 2. It's not going to change. Similarly, the variance is going to be exactly the same. And the standard deviation will be the same as well. Why? Think about it. You're shifting up the whole data set to observations. The actual spread of the data hasn't changed. Now, what's going to happen to the coefficient of variation, do you think? Is that going to stay the same? It's probably a little bit difficult, but it's going to actually decrease. Why is it going to decrease? The standard deviation is actually the same as the original data set. But the coefficient of variation decreases here because the mean has increased. The coefficient of variation decreases because the mean has increased. Does that make sense? Because that's the denominator. Now what happens if you multiply by 3? The mean's going to be multiplied by 3 as well. So it's going to be that 15 times 3, which is going to be 45. Now, what happens to the range, do you think? Well, the lowest observation is going to be multiplied by 5, and the highest observation gets multiplied by 5. The range actually gets multiplied by, the lowest observation gets multiplied by 3. The maximum observation gets multiplied by 3, so the range gets multiplied by 3 as well. So that's going to be 19 times 3, which is 57. Don't know why my italics are not working for me. Now the variance, this will be interesting. What happens to the variance? The variance gets multiplied by 9. What? Now, I can go to another sheet to explain this. Let's go back here. You might recall this. The variance of, say, 2x is equal to 4 times the variance of x. Whoops. Don't want to write equal to. Let me try that again. It's equal to 4 times the variance of x. This will be good. And the variance of 3x is equal to 9 times the variance of x. Okay, I've done it again. Anyway, you get the gist, right? It's going to be squared when you take it out the front. Okay? That's just it's a common rule when you're dealing with variances. So, let's go back. The variance is going to be that number to the times 9. And the standard deviation, again, is going to be the square root of that, which happens to be multiplied by 3. So the standard deviation gets multiplied by 3. The variance gets multiplied by 9 when you multiply each observation by 3. So sorry, I should have specified. When I'm saying multiply by 3, I'm saying every observation gets multiplied by 3. And our coefficient of variation, what do you think is going to happen to that? Let's go. Coefficient of variation is the standard deviation divided by the mean. It's the same. So interestingly, when we multiply every observation by 3, or by anything, the coefficient of variation stays the same. Okay. Let's go to question 2 now. I'm just going to scroll this up. No, that will not work. Okay, let's go to question 2. I might even make this a little bit larger for you so you can see what we're dealing with. In question 2, we've been given two stocks, Trust A and Trust B, or stocks or trusts. We've been asked to calculate the portfolio return for each year, where the portfolio is 50% in A and 50% in B. Simple enough. So my portfolio is just going to be the average of each of these two returns per year. Okay. Not particularly difficult, I would not think. Great. So there's the portfolio returns for each year. calculate the mean return and standard deviation of the portfolio. Okay, so let's do this. I'll go portfolio mean standard dev. Now, we saw how to calculate the standard deviation and mean in the previous example. So I'm not going to go over that again. You can confirm that the standard deviation is correct in each of these, but the mean for each of these, the average of the portfolio, is going to be 14. The standard dev, and to use Excel, you go stdev, and then you highlight the cells, is going to be 12.6. Now, again, I've calculated the standard deviation manually in the previous example. So if you want to try yourselves to calculate the standard deviation for this portfolio, by all means do it. Get more practice in. So there's the mean return, there's the standard deviation, and the coefficient of variation, coef of var, is going to be the standard deviation divided by the mean, which is 0.9019. Okay, cool. So I can now do, if I want to, trust A as well as trust B. And you'll have to forgive me because I have not formatted this appropriately before I began. That's okay. Now we can do the same for each of these. I can calculate the average of trust A. And again, if you want to do this by hand, by all means. Practice makes perfect with this stuff, and at some point you're going to need to calculate a standard deviation by hand, or even if you're not doing this from a university perspective, it's so useful to know how standard deviations are created, because it just, using numbers without understanding them is my pet peeve, and it just means that you don't actually know how to be malleable with your analysis. So allow me to just type some of this stuff in. Standard deviation for trust B, and the coefficient of variation for trust B is that standard dev divided by the mean. Okay, so the mean of the portfolio is 14. So that's percent return, presumably. The mean for trust A was 16, so it was higher. And the mean for trust B was 12 with the lower standard deviation. So this is very common. You often get a higher return, in the long run that is, for a higher standard deviation, meaning more risk. And you can see in trust A you get highs of say 42 and lows of minus 6.2, whereas for trust B you get highs of 27 and lows of minus 2.8. Okay, so the question now is, rank these three investments as to their return, riskiness, and coefficient of variation. Once we have all this stuff, it's super simple. Trust A has the highest return, then comes the portfolio, then comes trust B, and no surprise, the portfolio fits neatly in between trust A and trust B. The standard deviation of the portfolio again fits in between them, trust A being the more risky and trust B being more safe. And when I say more safe, it just means the returns are in a more confined spread. So that's pretty simple, really. We're going to get into some more complicated portfolio analysis in subsequent weeks, but for this week, that's it. And if you want to connect with any of the stuff I do, there are some more general videos on regression, as well as various distributions and other types of things on zstatistics.com. So feel free to check that out. On Facebook, just search for Z Statistics. It's a strange enough name that there's probably not going to be much else besides me using that name. And YouTube, it's ZED Statistics. And my email is zstatistics@gmail.com.